So today I will talk about a couple of layers. I would say that these are relatively easier for you guys to comprehend. One is the PDCP layer and other one is the RLC layer. Then I will reserve MAC layer uh, for a separate class because the MAC layer itself is quite important in the context of scheduling in cellular networks. So we'll talk about those separately. So I was showing you earlier also about what PDCP does. So again, at the high level, it does the compression of the headers, especially when you're using the IPv6 and IPv4 kind of headers. The header sizes are quite big, especially when you look at low data rate application like voice over IP, or when you take machine-to-machine communication, that means IoT traffic. The amount of the traffic that you are sending is so less, but the headers are becoming quite giant, right? So we wanted to use some header compression to reduce this. That is one main thing. And you do something called PDCP duplication, and also you do the routing at the PDCP layer. So why we have to do these routing and PDCP duplication is to support the dual connectivity and split bearers. If you recall, I was talking about dual connectivity and split bearers when I was talking about some of the deployment options for 5G. If you recall, the split bearer was discussed in the context of we have the 5G and 4G base stations where one of them could be the anchor. And once the traffic reaches one of these base stations, it can in turn split the traffic and send it over 5G link and also over the 5G radio or 4G wireless link. That is called split bearer. Dual connectivity is about your handset is connecting with more than one base station. That way, it can get higher speed and reliability can also improve. So for supporting these cases, we do this PDCP duplication and also routing in the PDCP layer. Okay. And we also do this, we require something called a duplicate detection, because when you are sending same data over the two links, your receiver should have the ability to detect and accept only one copy and reject other copy. That is good. That is you do only in the case of high reliability for some of the RLC use cases. And also PDCP does the reordering. That means guaranteeing the packet delivery in the order in which the sender is sending to the higher layers. In this case, the higher layer for the PDCP layer is the HDAP layer. It is optionally defined. If at all such a service is needed for some of the use cases, the PDCP layer can enable the reordering mechanism. And also it can do this duplicate transmission of the PDs over multiple logical channels. So what the meaning of this is, you can take the same packet and send it over two links, where I'm not talking about two different wireless links. These are the two logical links at the layer below, where PDCP layer works with something called a radio link control layer. I will talk about this later with small animation, then you will understand why we have to do this kind of duplication and how that kind of thing helps for RLC use cases. It also does the encryption of the messages and also does the integrated protection so that the messages are not tampered during the wireless transmission. Let's look at what PDCP layer is doing with this illustration. Look at so far what we discussed. We looked at HDAP layer. So HDAP layer takes the QoS flows and maps to something called radio bearers. So this is one, you can assume that this is one PDCP entity. So you need to have one PDCP entity for each radio bearer that is set up. So this example is the case where I have an HDAP entity from which I am getting one radio bearer. So we are mapping that radio bearer to one PDCP entity at the layer below HDAP. That is the case. So that at a high level you can think of, you are getting HDAP packets. Now the PDCP layer is taking HDAP packets. What PDCP does, you look at. First, it does something called sequence numbering. Basically, it is adding sequence numbers to the packet so that you can come to know in which packets are delivered and which packets are not delivered. After adding a sequence number to the packet that is received. It is also storing the packet in something called a retransmit buffer. So we have a buffer at PDCP layer in which the packet that is received from HDAP layer is stored. Then you take the packet, you do the header compression using ITF RFCs, whichever the thing that is relevant depending on the kind of application traffic that you are carrying. Then you also add the integrity check. Basically, you add MAC, message and authentication code. Then you do the encryption using AES kind of encryption protocol with the key that is agreed between the handset and the core network. And the PDCP layer also can add some control messages to ensure that what kind of messages are delivered and what are not delivered. So finally, we are creating the header. This header is the one that is added to the HDAP packet. So we have HDAP packet to which you are adding the PDCP header. So this is the one that you get after this is called PDCP PDU. So now I have the PDUs from the PDCP layer, which are now subjected to the routing or the duplication depending on the use case. So it is possible that you can take one PDCP entity and you can associate that with a maximum of 4 RLC entity as part of the release 16 of the 3GPP. I will come back and explain how you do the mapping of PDCP entity to the RLC entities and what is the benefit that you get by mapping them to 4 different RLCs when I discuss the RLC module later. But for time being in the slide, assume that we have 1:1 mapping between HDAP entity and PDCP entity for the one of the radio bearer that is coming from the HDAP layer. So at the receiver, you do the exact opposite. And because I was mentioning that it also does in-sequence delivery. In-sequence delivery to HDAP layer. So whenever, let's say if you are sending packet n plus 1, n plus 2, for whatever the reason, assume that the receiver has received n and it has received n plus 2 and n plus 1 has not received. And what basically the in-sequence delivery kind of says that is, the packet should be delivered only in the order only. And if needed, it also does the reordering so that they should be delivered. That is not that you deliver n plus 2 and after that you deliver n plus 1. That is not accepted. So whatever the packet delivered, that should be delivered only in the in sequence. Okay. And if you look at, I was mentioning about having the retransmit buffer at the sender side, and at the receiver side also you have the receive buffer, so that whenever you receive the packets out of order, you can kind of, that means let's say receiver has received these two, that means it has received n and n plus 2. So yeah, so it has received the things in order, but after that it may be getting n plus 1. So this is the kind of comes as part of the out of order case. So this is important, especially to deal with the case of the handovers. But in general, if the receiver is getting n and n plus 2, after that it is getting n plus 1, it won't be sending n plus 1 if we tell it has already transmitted n plus 2 to the higher layer. So before it is transmitting n plus 2 to the higher layer, if n plus 1 is coming, it is well and good. So it storing n and n plus 2 in the buffer for certain amount of the time. By the time the timer expires, if it has received n plus 1, then it is well and good, it sends everything. Otherwise, it goes ahead and sending n and n plus to the higher layer. That is the meaning of in-sequence delivery. And but there is no retransmissions as such at the PDCP layer, except for the case of handovers. Because for the handovers, we have to do the retransmissions. The sender side, we have this retransmit buffer. So I will explain that with this call flow diagram. So Ranjan, you want to ask something?
Yes, sir. So for the integrity check, why are we adding MAC? Shouldn't we add something like CRC or checksum?
Oh, no, no, CRC check is not for integrity check, right? That's why I said you guys should do course on cryptography. Then you understand the difference between CRC check and integrity check. CRC is
Okay.
only to detect the bit errors.
Yes.
And cryptographically, it is not a strong mechanism to check whether the data has been tampered or not. That means with non-zero probability, you can always tamper with the message and it can pass through your CRC check compared to
Yes.
the,
Yes. That's possible.
yes,
But
yes.
how is MAC going to? MAC is like our regular MAC address or something.
No, 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 no. Sorry. Okay, you misunderstood when I say MAC. It is a
Yes.
message authentication code. Did you hear
Okay.
about SHA-1, SHA-2,
Right.
MD5,
Right.
and other thing?
Yes. Yes.
These are the cryptographic techniques which basically generate cryptographically strong integrity messages which have extremely low probability of passing through all these checks.
Okay, sir. And one other thing, is this PDCP layer something like transport layer because the functions are almost similar?
What is see, we have the sequence numbers,
Yes,
and
sequence number. This.
we have that retransmit buffer. This retransmit is not for retransmitting the packets between sender and receiver. This is only in the extreme case of handovers that I will show in the following slides. Otherwise, PDCP layer doesn't take care of the reliable data delivery. So what I'm trying to say is that reliable data delivery is not defined here, as you see here. The TCP does the reliable data delivery. Here, there is no reliable data delivery. But again, still I am saying that
Right.
there is a retransmit buffer that I am just about to explain that is only there for handovers. Otherwise, reliable data delivery is actually the function of the RLC layer and the MAC layer, not the PDCP layer. So let me show
Okay.
you what is there as part of these retransmissions and why we need to have retransmit buffer even though we are not giving the reliable delivery as part of the PDCP layer. So this is example showing this is your old base station and this is your new base station, your G node B. So this is an example where, look at, we have the RRC reconfiguration established. Basically what it means is that handover took place. So I didn't explain what is handover and other thing, but at the conceptual level, it is like your handset is receiving weak signal from the currently associated base station and it is found a new base station with better SNR or SINR. So because of that, old base station has hand over the user equipment to the new base station so that the user equipment start getting the data transferred through the new base station the way it used to get through the old base station with the help of the core network. So for that, all the three entities have to talk with each other using RRC reconfiguration messages to establish the radio link between the base station, the new base station and the handset. That is what is being shown here as part of this RRC reconfiguration. Then look at what is happening. We use the XNAP protocol, which is the control plane protocol between the base stations. Okay, this is XNC. If you recall, two base stations can talk using XNC interface. So the sequence number status transfer is done from the old base station to the new base station. Basically, look at what it is doing. The base station is sending the list of the received uplink packets. The old base station is sending what are all the uplink packets that I have received from the handset. That it is sending to the new base station. List only. It is only giving the list. It is not actually sending the packets. The uplink packets, whatever the old base station has received in the uplink, that might have already transferred to the UPF and through the UPF to the data network, whatever that already happened. But the recently received uplink packets status is being passed on to the new base station. That is one thing. And look at what old base station is doing. It is also passing the buffered downlink packets and it is also passing the buffered uplink packets. Look at what is the buffered downlink packet. What is the meaning of buffered downlink packet? The base station has If you look at here, whatever is there in this buffer, that these are the buffered. These are the buffered downlink packets. That is the meaning of that. And each node will have both the entities. It has the PDCP transmitting entity, and each node will have PDCP receiving entity as well. Even though I'm showing you PDCP transmitter and receiver, let's say it could be your base station, it should be your handset. So in the downlink, this is what at the base station we are using the PDCP transmitting entity, and at the handset side you are using the PDCP receiving entity. But when your handset is transmitting, then what will happen? At the handset we'll be using the PDCP transmitting entity, and at the base station you will be using the PDCP receiving entity. So you can assume that we have one instance of PDCP transmitting entity and one instance of PDCP receiving entity at both the base station and at the user equipment for the radio bearer that it is part of. So that is the case. Now what is happening here is all the buffered packets that you see it here. So this is your old base station. I'm talking about the base station is talking with the user equipment. In this case, this base station is talking with the new base station. So the copy of the contents of the buffered retransferred buffer is transferred to the new base station. And whichever the packet that it has received from the handset, but which are not yet forwarded to the UPF, those are also kind of given to the new base station. Then look at what new base station is doing. It is telling to the user equipment that I have received these uplink packets from the old base station to the user equipment. Look at what the new base station is doing. Base station is telling to the user equipment that these are the recently received uplink packets to the user equipment. After that, your user equipment, see what it is doing. It might have already transmitted some packets. And now it is now very clear that even during the handover, these packets are successfully received by the old base station. So because of that, your handset can start discarding the buffered packets. Because when your handset is transmitting in uplink, then your handset also has kept its packet in its retransmit buffer. So that buffer is now emptied here by this particular process. That is the thing. Similarly, the user equipment is telling to the base station, the new base station, what are all the downlink packets that he has already received. After that, it checks what are the buffered downlink packet that it has received from the old base station, which is currently there with it. It checks, compare this one with this list, and whichever the things that are already kind of successfully received by the user equipment, it can discard, and only the rest of the packets which are not yet received by the user equipment, that new base station has to transmit over the radio link. So that's what you are seeing it here. All the undelivered downlink packets, that means these are the, like if you assume that I have 3 out of that, these 2 are already delivered, this is pending, only that part I have to send it. Similarly, user equipment also has a buffer, and if it has, let's say 4 out of that, 2 of them are already delivered, so that I can discard. All the remaining 2, it has to send it. That's the reason why we have the retransmit buffer. This buffer is not for reliable delivery. Typically, you need to keep the things that you are transmitting in the buffer only when you wanted to have acknowledgements and for reliable delivery. This is only for handover support. I don't know whether you are able to follow what I am saying or not. Is this clear? Why we are using the retransmit buffer in the PDCP layer?
Yes, sir, kind of clear. Yeah.
Yes, sir.
You just go through one more time. If you have any doubt, we can discuss one more time. So this slide is showing what is headed compression and what benefit that you get it. So because voice over IP uses these kind of protocols, IP, UDP and RTP thing, where you have the IP header if it is IPv4 it is 20 bytes, and if it is IPv6 it is 40 bytes. So UDP, can somebody tell me how many bytes? 8 bytes, and if it is RTP it is 12 bytes. That way, depending on whether you are using IPv4 or IPv6, header is 40 to 60 bytes. And a typical voice or payload, it is 32 bytes. To send a packet of 32 bytes, you are adding a header of 40 to 60 bytes. That is too much, especially when you are talking about supporting voice or IP applications or machine-to-machine applications like IoT traffic. To address that, IETF has defined multiple RFCs that you see it here. There are a bunch of RFCs which you can use it to compress these bunch of protocols together. And you can look at these RFCs to understand how they do it. But in general, how the compression works is when you're, let's say you have two entities, A and B. What they do is first packet, the first packet, you send it as it is without compression. This is the packet 1. What you do is for sending packet 2, you don't send packet 2 as it is. You don't do that. Do you know what to do? You send P2 minus P1. And because if you look at IPv4 and IPv6 case, we have 40 to 60 bytes. In most of the cases, the difference between the first packet and second packet is order of 4 to 6 bytes. That way, the savings that you get are tremendous. And those who have studied how the MPEG compression or H.264 compression, there also you do exactly the same thing. You take first video frame and you send it as it is, rather than sending the second video frame. You take the difference of the first and second video frames, and that way you can able to significantly cut down the amount of the bandwidth that is required to send video traffic. Otherwise, video traffic kills all the internet bandwidth. Thanks to this MPEG and H.264 standard, they achieve significant amount of saving. Of course, there comes under something called lossy compression. Whereas here, when I'm talking about the ROHC, I'm talking about lossless compression, because lossy compression is okay for video and audio kind of applications, because our humans can able to tolerate certain loss and can interpret what is happening. But this is not the case when you're talking about these headers. Even if one bit is corrupted, then you have the FCS failures and you have to retransmit everything. So an example is shown here. It says that when you don't do the IPv4 and IPv6 based header compression, the overheads are in the order of 188 to 125%, depending on whether you're using IPv6 or IPv4. But after you do the ROSC, the overheads have come down all the way from 188% to 12% to 80%, 18%. So now I'll talk about the RLC layer.
So there's like Vasudev, I think, is waiting. Can you admit him in the classroom?
Oh, who is that?
Vasudev, I think.
Okay. Viren, can you admit him, or only I have to admit?
Sir, only you can admit, sir, actually.
Oh, is
because
it? Okay, now I admit it.
So you clicked on don't entry.
Oh, there are multiple people. What is happening? What I have to do?
Sir, earlier you clicked deny entry instead of admit.
Oh, really? Okay. Vasudev, are you able to join now?
Yes, sir, I am. I'm in the middle now. Thank you.
What happened? Your network went down or what?
Yeah, I got a call, so I got disconnected from the meeting.
Oh, you are on hotspot, is it?
Yes, sir.
Yeah, so that is a case of priority. Voice is given more priority over data, right?
Yeah.
But they don't know that you are in even more high priority session. Yeah. Okay.
Sir, when we were talking about compression, you showed some table that has 3 columns. Yeah. Sir, in this RFCs that are in the last, are they define the compression techniques?
Yeah. Basically, they talk about how, even let's say, for example, if you take the first one, it says that you are not doing any compression, but the second one talks about when you have the combination of RTP, UDP, and IP header, how you should go about doing the compression. That means, again, at the conceptual level, what I said happens, where you send the first packet as it is. The second packet is the difference between the first packet and second packet. So they come up with different optimizations in the case where there are packet loss and other thing as well. Yeah, so they talk about how to do the compression. Again, this is like a lossless compression. It is not the compression that you do in when you are encoding the video traffic or video frames. Yeah, something else similar, but it is meant for a different purpose.
Okay, sir.
Okay, so let me explain over the next half an hour what is the role of RLC layer. And I think Suranjan, you were mentioning earlier about the PDCP is providing something what TCP does. That is not true. But if you want to look at and see, is there any other layer that does something similar to TCP at the MAC, at the data link layer, or at the layer 2 is the RLC layer. So you can think of RLC layer as a kind of equivalent. Again, I'm not saying that that is the same as the TCP. It is a kind of equivalent to what TCP does. The reason why I'm saying it is equivalent to TCP is RLC also does the reliable data delivery. Okay. So that way we say that RLC protocol maintains data link between user equipment and the base station. And it has interestingly 3 different modes of operation. So one is the transparent mode, second one is unacknowledgement mode, other one is the acknowledgement mode. Whenever I mentioned about this is equivalent to TCP, is when it is operating in AM mode, not when it is operating in TM or UM mode. Okay. And what happens is when you have the data that is coming to RLC layer from PDCP layer, what RLC layer does is it takes the packets coming from the PDCP layer and gives in turn the packet to the MAC layer, where the MAC layer, depending on what the scheduling decision is, on how much amount of the radio resources each QoS flow should be given, depending on that, you do something similar to the TCP, where TCP also, depending on what is the current congestion window size, it decides from its outgoing TCP buffer, number of bytes that it want to send, and add the TCP header to that and send it over the network. Something similar happens even in the case of RLC layer, where RLC layer gets the PDCP packets and it stores in its own buffer. And whenever the MAC layer is decided to give to one particular user or one particular QoS flow certain amount of resources, that much amount of the data from this layer is taken out and packaged as a MAC frame and send it over the air. And one major difference between RLC in 4G and 5G is there is no concatenation in 5G, unlike in 4G. Reason why they have removed the concatenation is to reduce the latency. When the concatenation is good, especially when you have small size packets, you can able to save the radio resources, but the concatenation also delays the transmission of the data. So because we are talking about some of the URLC use cases, they have removed the concatenation. So if you have to tell you in summary, the protocols that you have, that is PDCP layer and RLC layer, have been kind of simplified in 5G as compared to the 4G. So the 4G PDCP and RLC layers are even more complex and more powerful than what you have right now in the 5G. So that is the thing. So if you know what these layers are doing in 4G, you already know what they do in 5G with a few exceptions. And one other thing that is not defined in 5G, which is there in the 4G, is in the 4G, RLC does the reordering. That means it guarantees in sequence delivery. But in 5G, RLC layer doesn't do any reordering. If at all you want to do have the reordering, so that means guaranteeing the in sequence delivery, you have to rely on the PDCP layer. So PDCP does the in-sequence guarantee, but RLC layer no longer does the in-sequence delivery. And we also have something called retransmission protocol in the AM mode, because in the AM mode, we wanted to guarantee the reliability like what you get in the TCP. Then you have to store the transmitted packet in the buffer and wait till you get the acknowledgement. Okay. And even though I'm saying that RLC layer does the reliable data delivery, but it does to a greater extent. But if you really want to have the ultimate reliability, then you have to rely on the MAC layer, because at the MAC layer we have something called hybrid ARQ, using which we can also have reliability. That means if you have a TCP flow from your application, so then you have the TCP doing the retransmissions for achieving reliability. Then you have the PDCP layer, so not PDCP layer, sorry, the RLC layer, which is configured in the AM mode. We try to guarantee the reliability. Then you have the MAC layer with the hybrid ARQ, which also, that means we have the retransmissions defined at 3 different layers in the protocol stack for applications. Your packet, even if it is get lost at one of the layers, even after multiple retransmissions, it is a higher chance that higher layers can start recovering from those losses by retransmitting. So that way we have 3 retransmissions mechanisms when it comes to the TCP flows, at the TCP layer and at RLC layer and also at the MAC layer. So what you see is the this is like it is at the base station side, and this is at the user side, how the protocol stack of the RLC layer looks like. So yeah, you can assume this is the higher layer. From the higher layer, we are getting the packets to the RLC layer. Look at what RLC layer is having. It has a different entities. You can see it has one entity for transmitting in transparent mode. It has one entity for receiving in transparent mode. It has another entity for transmitting in UM mode, that is unacknowledgement mode. It has another entity for receiving in unacknowledgement mode, and AM mode is bidirectional. So because of that, for both transmitting and receiving, we have only one entity defined here. So then it pushes the packet down to the lower layers. In this case, lower layer is the MAC layer. So this is at the UV side, and yeah, this could be our MAC layer at the UV. And from the MAC layer, the packet will go to the respective entities at the RLC layer. So let me show you why we need to have 3 different modes of RLC defined in 4G and also in 5G. So this picture is exactly same in 4G and 5G. Look at, okay, looks like somebody again went out of the network, is it? Supriya, okay. Hello, Supriya, are you able to join now? Okay, I think she is able to join. Okay. So look at why we need to have 3 modes. I was mentioning we have the TM mode, that is transparent mode, then we have the UM mode, then we have the AM mode. So TM mode is the one that is used by the RRC layer for the signaling messages. That means signaling messages that are coming from the RRC layer don't use RLC. For that matter, they also don't use a PDCP. Is that clear? Let's say I was talking about the case where you are establishing a new QoS flow. For that, you have to establish a bearer or you have to modify the existing bearer. In that case, then we have to send these messages, RRC messages from the base station to the handset. So these RRC messages, which are generated at the RRC layer, are directly sent it to the MAC layer without adding PDCP header, without adding RLC header. That is what you can see from the illustration. RRC packets are directly sent to the MAC layer Even though I'm saying we have this entity, the transparent mode RLC transmitter, it doesn't do anything. It simply takes the packet and push it down without adding any header. That's it. And when it comes to the other traffic, that means RRC messages which require reliability and even the user traffic, they come over the PDCP. Okay, and these PDCP packets can either use an acknowledgement mode of the RLC when you don't require reliability. When you require reliability, use the AM mode of the RLC. So that way, look at the case here. Voice over IP, email. Does it make sense? It is fuse flow request or whatever it is. So look at the three different cases that I am showing it. One is modifying or establishing a QoS flow. Other one is sending voice over IP traffic, and other one is sending email or file transfers. File transfers and emails require reliable delivery. That's the reason why we are using the AM mode of the RLC. But voice over IP and even the video conferencing, they don't require reliable delivery, but they want quick delivery of the messages with certain loss rate guarantees and jitter guarantees. For that reason, rather than using AM mode, you can use unacknowledgement mode. And look at the point that I was trying to show earlier. Each PDCP entity can be associated with a maximum of 4 RLC entities, where 2 out of the 4 are for transmitting and 2 out of the 4 are for reception, using which you can support dual connectivity and also you can support PDCP duplication. So did you guys able to understand what I was trying to show here? Maybe I will use a small example. Oops, color or choice.
Sir,
So the example that I'm showing is when you have the PDCP, this can be associated with 4 different RLC instances. TX1, RX1, TX2, and RX2. Okay, I should not draw double arrow. I think for this is the transmit, and this should be this way. This is the transmit. Yeah, this should be this way. Yeah. So Ranjan, you were trying to say something. What is it?
so I was saying that in unacknowledged mode, so it is basically like UDP or something like that, because
Yes,
it
yes.
doesn't record reliability.
Yes, yeah, you are right. That's the reason why I'm showing that can be used for, but again, don't confuse with this layer with the UDP layer. UDP layer is anyway there, that is added to the packet for voice over IP. But yeah, the functionality wise, yeah, logically, it is doing something similar to the what UDP is doing, right?
Right.
And that's the reason why we are using it for voice over IP and video traffic. So can you able to see my cartoon here? I'm showing you I have a PDCP entity. So this entity is set up for one data. For a data radio bearer, which is given by the SDAP layer, we have established one PDCP entity. I'm showing you here that this PDCP entity can be associated with 4 different RLC entity, where 2 of them are for transmission and 2 of them are for reception. So look at why we are to do that. So there are 2 reasons why we want to do that. One is the PDCP duplication. So this is important for your LLC case. So can you try to understand what I'm trying to say? As the name says, I can send a packet. Let's say I have packet 1. Okay. I will send the packet 1 from the PDCP layer over this RLC instance and this RLC instance, where these two RLC instances that you see it here, part of same base station, are different base stations. What does that mean? Look at our the example of we have the master cell group and the secondary cell group, where the master cell group got the PDCP packet from higher layer. Then what it can do? It can create 2 copies of, sorry, oops, I think I wrote P2, it should be P1 again. Duplication means you are sending the same copy on 2 different RLC instances, where I can assign to 2 different RLC instances that belongs to the same base station, or they can be belonging to 2 different base stations. That means this is also with the same base station, like if it is, let's say, G node B, this is on the G node B1. This is also on the G node B1. Or this could be on the G node B2. If it is on G node B2, it will become more like a dual connectivity. And if it is on the same G node B rather than the second G node B, if you are sending to the same G node B, basically what you are saying is that each packet you are sending 2 times to the RLC layer. Then the RLC layer in turn send it to the MAC layer. So your MAC layer is also sending the same packet 2 times over the air. So why we do that? That you do it when you wanted to get extremely high reliability to support some of the use cases of autonomous navigation and industry 4.0 kind of cases, where you want 99.9999 reliability. Oops, again, looks like somebody else went out. Is it? Oh, Ranjit wanted to ask something, is it?
Yes, sir.
Ah,
Sir,
what?
isn't this contradictory like ultra reliability and low latency? For reliability, we are duplicating. Doesn't that increase the number of packets and eventually increase the latency?
Yeah, you are right, but you can also think of this way, right? Take the example where you are using the 2 different base stations to send URLC traffic. Then what do you say?
Okay, if it is 2 different base stations, then yeah, this condition is.
Then what you can, what's more likely will happen is at the end of the day, you will get through one of them faster than other one. You can discard the duplicate copy. That is one thing. But even when you take the same base station, still I'm talking here at the RLC layer. I don't know what the MAC layer is doing. It could be the case that the MAC layer has assigned 2 different logical channels, where one of the channel maybe, see, you assign these radio resources with a certain MCS. It so happened that the MCS that was assigned and the packet that you transmitted, because of some bit errors, maybe one of the 2 packet may got lost and other thing got delivered. That improves the reliability. And what MAC layer does is, because it is important, even it will retransmit the other packet that got lost. That way the retransmitted packet will come later, but since already it got the first packet through other link, it is end up getting on a faster mode. You are right in a sense that if we are trying to use the same base station resources, it may not appear like you are reducing the latency, but you can think in this way as well, because at the end of the day, the MAC layer also does a lot of things interestingly to be able to reduce the latency and improve the reliability.
Okay, sir. Sir, one more query. This RLC is actually in the layer 2, right? RLC and MAC.
And all four of them are in
All
the
four
layer,
are in the layer 2, right?
layer
sir?
2. These are the layer 2 protocols, yes.
Then why do we need to have this retransmission in RLC? We all anyway we have it in the MAC layer, right? Hybrid ARQ.
Yes, in fact, that is one of the interesting question that to ask. See, if you look at the way I'm showing it, I think not here. I think if you come back here, if you look at here, if you see the thing in this illustration, it is not that RLC always giving the reliability guarantees by retransmissions, only in one of the mode. So it is up to the applications and to the operator to decide whether to enable reliable delivery by choosing AM mode in the RLC, because as you said rightly, MAC layer is already doing the hybrid IRQ and guaranteeing the reliability. That means in the extreme case, you expect reliability rather than all the way asking the TCP to retransmit, then only you enable the MAC layer reliability and EM mode reliability at the RLC layer. Otherwise, you leave with the MAC layer reliability with hybrid IRQ by choosing the unacknowledgement mode of the RLC.
Okay, sir.
Hmm?
Yeah. Thank you.
So these are the choices that are defined. Again, depending on the use case, one can configure either way. And also nobody knows whether it is always the TCP that is trying to do the reliability, right? So as I was mentioning that 5G can also transport Ethernet frames. And Ethernet frames, anyway, they won't be taken care by the application, right? Because these are the just Ethernet frames. Then having the reliability at the RLC and MAC layer may be good for such transport of the Ethernet frames over the 5G networks.
Okay. So these are like the various options given.
Yes. Yeah. So what I'm showing is the kind of a framework or the platform that is defined by the 3GPP. Again, yeah, one can come up with different algorithms and solutions exploiting these to realize different applications and provide various services.
Okay, sorry. Okay. Thank you.
And okay, so whatever I was showing you earlier about the transparent mode is explained here. So transparent mode, it doesn't do anything. Okay, RLC PDU is nothing but RLC SDU containing an RRC message. That's all. So it doesn't do segmentation. It doesn't do the ARQ. And the upper layer for RLC TM mode is the RRC, not the PDCP. Okay, and it supports only the unidirectional radio bearers. This is how the flow looks like. You take the RRC messages and you send it to the MAC layer. And at the receiver you do. But again, you may be wondering why we need to have the transmit buffer. Can somebody think why there is a transmit buffer here?
Due to speed mismatch.
Sir, it needs to maintain reliable delivery, right? So for that.
No, this is the transparent mode, right? Transparent mode, there is no reliability.
Yeah, sorry, sir.
Sir, if the higher layer is generating data at a rate which cannot be handled by the lower layer.
So you're talking about flow control, is it?
Yes, sir.
So not truly a flow control, but if you look at, in this case, RLC layer is sending its packet to the MAC layer, right? So all of you know, right? The MAC layer has MAC queues, right? The MAC queues are actually maintained in the RLC layer. So that means the transmit buffer, whatever that you are seeing it here, is nothing but your MAC queue. So you may be wondering why we need to have MAC queue. I think it is something related to getting the prioritized transmission of the data by getting the scheduling resources. So yes, your RRC layer wanted to send the messages by bypassing PDCP and RLC and giving it to the MAC layer. But you have to wait till the MAC layer takes the packets and put it on the channel, right? Till that time, we need some temporary place to hold these messages. So that is the reason why we have the transmit buffer. So this buffer, you can treat it like MAC queue, which is maintained inside RLC layer. And it carries, we use this transparent mode to carry these 3 channels. I will come back and explain what are all these channels, but at the high level, you can assume that these channels carry the broadcast information. So all the information about what is the cell ID, what is the configured frequency, and what is the transmit power allowed, and what are the modulation schemes allowed. All that information is carried in the broadcast common control channel. When you are getting incoming call, you get the paging messages, so which are nothing but RRC messages, which have to be transmitted without any of the headers and send it directly to the MAC. MAC layer also gives more priority to these messages because these are the kind of signaling messages. Without that, network cannot function properly. Then we have the unacknowledgement mode. So as the name says, this is also not meant for reliable delivery because there's no acknowledgements involved here, but we use it for sending application traffic that is sensitive to the delay. Like I was mentioning, for voice over IP or video conferencing, or you can also use it for RLC traffic. And here also, because there's unacknowledgement mode, there is no ARQ involved. But the physical layer can guarantee the low bit rate by means of hybrid ARQ and using the lower modulation and coding scheme with PDCP duplication. So try to comprehend what I'm trying to say, that even though the unacknowledgement mode is not having any ARQ to guarantee the reliability delivery, fortunately we have the hybrid ARQ running at the MAC layer, which can guarantee the reliability delivery for the applications like voice over IP. How it can guarantee? It can apply things like reducing the modulation and coding scheme. That way you can increase the probability of the reception. And you can also create multiple copies of the same message. That is nothing but the PDCP duplication. That way you can improve the reliability of the message. These are the kind of tricks that you can apply, especially for RLC traffic, to be able to ensure that it is delivered quickly, even though we are using the unacknowledgement mode, where the reliability is not important, but the quick delivery is important. But for voice over IP, simply using a hybrid IQ at the MAC layer is sufficient, where you can use an unacknowledgement mode at the RLC layer. So look at what PDCP layer is doing it here. It is generating a header and putting the packet in the transmit buffer, and the packet size is bigger, and it is doing the segmentation. And whenever it is doing the segmentation, then the packet header has to be modified. That is what it is being done here. Finally, we have a header that is created and that is added to the packet, and it is keeping the packet ready in this RLC buffer, so that whenever the MAC layer decides to ask the packets from RLC, the appropriate number of packets can be taken from the RLC buffer and given to the MAC for sending it over the air. So this is used for dedicated traffic channel, that is to carry all kind of user traffic. And we also have the receiving instance at each node. It does exactly the opposite. Reassembly is required whenever you do the segmentation. So let's look at how the segmentation really occur, and for that matter, why do we need to have a segmentation? I was mentioning earlier that RLC doesn't do concatenation to save the time, because concatenation means you have to really do the job of packing multiple packets. And also when you are trying to concatenate, let's say you are asked to pack multiple packets together and send it, but you want to know the size of the payload that you wanted to send. That is not known many times till the scheduler decides what is the kind of thing that you can send it in the uplink. So that's the reason why the concatenation is removed in 5G. It was earlier there in 4G. And what you are seeing here is about how we can do the segmentation when you are having large size packets. But in general, the way the PDCP layer works is this way. Maybe I will try to explain. Or I have a small, okay, maybe I think this slide is suffice for my requirement. Look at this example where we have the two radio bearers, X and Y. For the radio bearer X, we have one HDAP instance that is created, and similarly, we have another HDAP instance that is created for radio bearer Y. Then we have, in this example, it is simpler. We am showing these HDAP packets are sent it to the PDCP layer where we are adding the PDCP header. These are all the user traffic. These are not the signaling messages. Then the RLC layer is adding its own header. But now look at what RLC is doing here. If you look at very carefully, so this is 1, if I call it as 2, and this is 3. And if I call it as 1, and this is 2, and this is 3, and this is 4. Look at what is happening here. RLC layer has taken the PDCP SDU 1 and 2 and simply added its RLC header. But when it comes to the PDCP SDU 3, it has done the segmentation of that into 2 parts and it taken a part of that is called SDU segment 3. And these are the 3 things that are kind of packed together and send it as part of one MAC PDU in a transport block to the physical layer. So how it really happens is the MAC layer informs RLC that it can send, say, 1000 bytes. And assume that this is 400. Okay, so this is 400 bytes. This is also 400 bytes for simplicity. This is also 400 bytes. So now we understood, right, why we have to do the segmentation. You want to ensure that this total is only 1000 bytes. So what you are doing is you are taking the as many PDUs as possible and adding the RLC header, and whatever the leftover that you have, that you are trying to fill out by taking another PDCP SDU, or sorry, PDCP PDU, and segmenting in a manner that you can able to use the remaining amount of the data to send it over the MAC channel. Other option that you can think of is doing the padding. But doing the padding basically means that you are actually wasting the spectral efficiency. Because in this case, I can send 1000 bytes, I can put 800 bytes and add the 200 bytes of padding, which is kind of wasting the radio resources. So rather than that, what I'm doing is I'm taking another PDU and segmenting it to 2 parts. And another important thing that happens is this header that is pre-calculated. This is also pre-calculated. And because we are doing this is also pre-calculated actually, that means we have unsegmented version will be there. That means originally we have this one H and RLC SDU, we'll have that thing. So initially we'll have this one which is unsegmented. But because the scheduler has given only 1000 bytes, I cannot use this header and send it this packet of 400 bytes. What I'm doing is I'm creating 2 segments, that is segment 3 and 4 of 200 bytes each. For that, so this header has to be modified and send it. And here there is no header, I have to create a new header. But only these 1000 bytes are sent in the current scheduling interval. So you can assume that scheduling interval is like 1 millisecond. So that means right now the base station has decided to take these 2 packets and 1 segment together and has created a transport block of 1000 bytes. For 2 of them, the pre-calculated headers are available. For the third one, it has to modify the header because now we have brought the segmentation into picture. And for the rest of the part, that is the segment 4, a new header has to be created. But for that anyway, we have a lot of time because the segment 4 will be sent in the next scheduling interval. For that, you have another 1 millisecond. So that's how it tries to remove the concatenation and also try to pre-calculate the headers so that by the time you get the scheduling grant, you are ready to pack as many number of RLC packets and send it over the transport block at the MAC layer. So that way we are kind of reducing a lot of latency and trying to make 5G as a versatile technology to cater to different kind of use cases where some of them are like RLC use cases. Maybe I will stop it here. I think we are already spent a lot of time today. I will maybe repeat some of these topics again in next class, but I wanted to go through these videos before you ask any doubts in the class on Tuesday.